All right, so we're going to continue our journey in Chapter 2 on determinants. And we're looking at now Section 2.2, Evaluating Determinants by Row Reduction. So you'll see that we're now on the Section 2 out of 3 in Chapter 2. So just to remind you, we're only going to be doing 3 sections in Chapter 2. So the objective of this section is to show how to evaluate a determinant by reducing the associated matrix to row echelon form. So we know all about how to do that. So in general, this method requires a lot less computation than cofactor expansion. And so it is the method of choice for large matrices. So we're going to be exploring reducing the associated matrix to a row echelon form. So hopefully that should be a review for you from Chapter 1. And so we're going to be doing this in order to evaluate determinants. So we're going to get to additional methods to evaluate determinants. So that brings us to our first theorem in this section. Theorem 2.2.1 says let A be a square matrix. If A has a row of zeros or a column of zeros, then the determinant of A equals 0. So lo and behold, we have this example matrix right here, and look at all those zeros. So we can automatically assume that the determinant is 0. We don't need to do any calculations. So what are you going to do when you look at a matrix? One of the first things you should look for is, does it have a row or column of zeros? And if it does, then you're like, I don't need to do any calculations. So I hope that will be a nice trick to look for, as well as being a theorem. So our next theorem is 2.2.2, and it says that let A be a square matrix, then the determinant of A equals the transpose of A, the determinant of the transpose of A. So here, if we look here and we see that A has a determinant of 0, so here that's a nice, quickly we can see this by inspection. So here, let me get my pen working here. If we quickly look at this column of zeros and we can say the determinant of A here equals 0. So I know in this situation that that is also going to equal the determinant of the transpose of A. And so that also in this instance is going to equal 0. Here for B though, let's go ahead and look at that. So we have for B, we know that the determinant of B is going to be 5 times 1 minus 7 times 2, and that's going to give us 5 minus 14. It's going to give us a negative 9. Then, if we want to go ahead and prove this theorem, we would go ahead and look at the transpose of B, and that would be, if you remember, what are you going to do? You're basically going to interchange your rows and your columns. So that means that now your transpose of B is 5 and 7 in the first column, and then the second column is going to be 2 and 1. And then now, if we take the determinant of the transpose of B, that is going to equal, once again, 5 times 1, and then minus, now, 2 times 7. What are we going to end up with? The same thing over again. So, as you can see, the determinant of B equaled the determinant of the transpose of B. All right, so from there, now that we've had a couple theorems under our belt, the next set of theorems in the text is Theorem 2.2.3. And so with these, instead of offering up a lot of different proofs, they went ahead and gave you a table to illustrate these ideas. And so we're going to look at each of these ideas one by one. So we're going to look at A, B, and C. So if we look at, is the idea that we can conduct elementary row operations, once again. And so the first relationship that they want to point out is that if you look at matrix A, B was formed by multiplying the first row of A by a scalar k, or a non-zero constant. So here you'll just see for B, it has the non-zero constant k just multiplied by this first row. So keep in mind that relationship. So then that means that the determinant of B is going to equal a scalar k times the determinant of A. So think about this elementary row operation and multiply. So going from A to B in this instance here, they just multiplied a row by a non-zero constant k. So this first row here. And they're setting up the relationship that the determinant of B equals k times the determinant of A. Our next relationship, or actually let's go ahead and do an example first. So if we look at this example, we have here that B was formed by multiplying just the second row here by a non-zero scalar k. In this instance, it happened to be k equals 2, right? So that what this means is that the determinant of B in this instance is going to equal 2 times the determinant of A, by what I just showed you from before in that relationship. So here we're going to look at another elementary row operation that we're familiar with. And so if you look at going from matrix A to matrix B here, the first and second rows were interchanged. So the first and second rows were interchanged. So here, now you have these two were interchanged. So now you have the A21, A22, and A23 at the top. Whereas before, in A, they were here. So I'll go ahead and draw those arrows in there. And so the relationship that you should get from this is that now the determinant of B equals the negative determinant of A. So that is a new relationship that they are giving us. And so here is an example. So here, if you'll notice, the rows of A were interchanged. So here, the determinant of B now equals negative determinant of A. So if we wanted to go a little bit deeper into this, we look at determinant B. So here we have 3 times 2 minus 4 times 1. So all of this equals 6 minus 4. That's going to equal 2 for determinant B. Determinant A, we're going to have, so I'll make a little arrow here, make a little arrow here. For determinant A, we're going to have 1 times 4 minus 2 times 3. So what is that? 4 minus 6? That equals negative 2. So lo and behold, that relationship holds up. And now for our third elementary row operation. With this relationship, you can see that matrix B here on the right was formed by multiplying the second row. So this second row of A was multiplied by a non-scalar k and added to the first row. So here we got k times A21. That's added up here to the first row, to the A11. So you'll notice that that was done across. And so now they have the relationship that the determinant of B equals the determinant of A. So you're going to want to remember these different elementary row operations. And then what kind of relationships between the determinants does that now form? So let's look at an example with that one. So what did we do with this example? If you notice, 2 times, so 2 times this first row was added to the third row in order to get B, the matrix B. So 1 times 2 plus 3, that equals 5. 2 times 2 plus 4, that equals your 8. So now for this relationship, we should have that determinant B, in this instance, equals determinant A. So for determinant B, that is going to equal our 1 times 8 minus our 5 times 2. And that's going to be 8 minus 10. That is going to be negative 2. And here for determinant A, we're going to have equals 1 times 4 minus 2 times 3. So here that's going to equal 4 minus 6. Oh, wow. That one also equals negative 2. So these are kind of cool, really cool relationships between the different row operations and what they mean in terms of the determinant relationships. So definitely make sure that you look at table 1. This is going to be important for you. So make sure to check that out. So I have it here on this slide, so you'll want to go ahead and take note of this. So here I'll go ahead and make note that this is table 1 in case you want to bookmark this slide. And don't forget that it talks about theorem 2.2.3. So table 1 is an illustration of theorem 2.2.3. So here we went through each of these scenarios, A, B, and C. So this leads us to our next theorem, 2.2.4, about elementary matrices. You know elementary matrices are always special, and so here's some other things to take note of. So let's suppose that E is an n by n elementary matrix. So if E results from multiplying a row of an identity matrix by a non-zero number k, then the determinant of E equals k. So that is going to be very useful to us. And then if E results from interchanging 2 rows of an identity matrix, then the determinant E equals negative 1. And if E results from adding a multiple of 1 row of an identity matrix to another, then the determinant of E equals 1. So we're taking those same operations that we did before on a non-elementary matrix, and now we're applying those same row operations to an elementary matrix, and now looking at that new determinant relationship. So these are going to be useful to us as well. So we can quickly calculate these determinants when we look at by inspection at what kind of matrix do we have. So here we'll look at example 1. So if you notice in example 1, this first matrix, so this was created by multiplying the second row of an identity matrix by 3. So here our k was 3. So you can see here this second row was multiplied by k. In this instance was 3. Don't forget the identity matrix here, we would notate it by calling it I4 because it's a 4 by 4 identity matrix. So here in this case we can look at A up here under theorem 2.2.4. It says, so if we multiply an elementary matrix, if E results from multiplying a row, an identity matrix, by non-zero number k, the determinant of E, in this case, is going to be k. So here we recognize in this instance our k was 3. So keep in mind, the identity matrix that was multiplied by was an I4, and then this is now the resulting E. And our k was 3, and so now our determinant of E is going to be 3. So in the next one, part B of theorem 2.2.4, it says if E results from interchanging 2 rows of an identity matrix, then the determinant of E equals negative 1. So let's look at what in the world did we interchange. So it looks like this first row and this last row of the identity matrix was interchanged to get this elementary matrix. And so then it's telling us now that determinant of E, then equals -1. All we did was interchange the first and last row, but now we know the determinant equals to -1. And then for our last relationship in C, says if E results from adding a multiple of one of the rows of an identity matrix to another, then that determinant of that elementary matrix equals 1. So here we multiplied 7 times this last row, and added it to the first to get this new elementary matrix. And so now we know from this theorem that the determinant of E equals 1. So if we move on to our next theorem, this is another easy one that's really handy. It's all about matrices with proportional rows or columns. So theorem 2.2.5 says if A is a square matrix with 2 proportional rows or 2 proportional columns, then the determinant of A equals 0. So this is another theorem that we should be able to recognize upon inspection. So let's look at an example of this. So here we see that if you look at this column 1 here, you will see that it is proportional to this second column here, because what you did was multiplied the first column by -4 to get to the second column. So multiplied by -4. So those two columns are proportional. So go ahead and look at this next example. This is a bigger matrix. We got a 4 by 4. So what do you think? Do you think the determinant is 0? Can you find any proportional rows or proportional columns? I have to say, maybe not at first glance. You might not see it right away. But I would like to draw your attention to the top row and the bottom row here. And they are proportional because you're basically multiplying the top row. So here, the top row was multiplied by -3. So those two rows are in proportion to each other by a factor of -3. So we would easily look at both of these matrices and we would say, guess what? The determinant of these equals 0 because they have those proportional rows or columns. So I hope you're paying attention to these different theorems, because I would expect on a quiz, hint hint, that you would be able to look at a matrix by inspection and be able to determine its determinant just by looking at it and thinking about it. You wouldn't even really need to make any kind of sophisticated calculations. So keep that in mind. And then the point of this section is that we're trying to have a method for having a lot less work in figuring out our determinant. And so we're going to go back to our elementary row operations to kind of save us some work, because we'd rather not have to go through all this cofactor expansion if we can help it. So we're going to be looking at row reduction in order to determine the value of our determinants. So I want you to kind of think of these 3 steps. So that first step, in order to compute our determinants, we're going to reduce a given matrix to an upper triangular form. So do you remember what an upper triangular means? So that's what we're going to try to get to that form. So we're going to try to reduce it to that form by elementary row operations. And then we want to compute the determinant of the upper triangular matrix. So that should be a very easy computation. And then we're going to relate the determinant back to the original matrix. So let's take a look at how this is going to work. So for this matrix here that you see in example 3, we are trying to determine what is the determinant of A. So we're trying to compute this, or you could say evaluate this. Alright, so when we look at example 3 in detail, because we know we're going to be calculating the determinant of A, one of the first things that we're going to want to do to reduce A to row echelon form, which is going to be our upper triangle, is that we want to swap out the first and second rows. We want to interchange those two. So the first and second rows, so these two are going to be interchanged right here. So here we have the new determinant of A is going to equal 3, negative 6, 9, 0, 1, 5, and 2, 6, 1. Now, am I forgetting anything? Yes, I am. I need to put in a negative sign here because, you ask, I have interchanged the rows. And so when that happens, you have to remember your relationship from your table 1, that when you go ahead and interchange rows, that the determinant of B equals negative determinant of A. So this now has a negative sign in front of it when we went from this matrix up here to down here. So then, now that we have this form, the next thing we're going to do to reduce this even further to row echelon form is that we can take out a common factor of 3 from the first row. So we're going to take out a common factor of 3 from this first row. So we have the new determinant that's going to equal a negative 3. And we've taken that factor out, so this top row is now 1, negative 2, and 3. And this is going to be 0, 1, and 5. And this will be 2, 6, and 1. And we're going to be making use of that relationship from table 1 that says determinant of B equals K times determinant of A. So we've pulled out that scalar 3 from that first row. Alright, so now what are we going to do? So, the next thing to do, in order to reduce this further, as you will note, is what we did is we did negative 2 times the first row, and we added to the third row. My handwriting is very poor these days. So you'll notice this matrix here that we have, so we did negative 2 times this first row, added it to the second row to get this resulting matrix. So that's great that we did that. And when we do that, remember our relationship determinant B equals the determinant of A from your table 1. But guess what? We can obviously reduce this even further. So you guessed it. If we take 10 times, or I should say negative 10 times that second row, so negative 10 times this second row, and added it to the third row, well, you know what, we're conducting our row operations to do this. So here is our next form of the matrix. So we have now gotten rid of that 10 in the third row. This has now become a 0. So now we have 2 leading ones at the moment. So what are we going to do now? We're going to take out, you guessed it, how are we going to get a leading 1 in this position? So you know what we're going to do? We're going to take out a common factor. So take out a common factor of negative 55. And what does this now look like? Should now be down to this. We've taken out that common factor of negative 55. And don't forget your relationship, once again from table 1, that the determinant of B equals K times the determinant of A. So now we have an upper triangle. So now we have this in row echelon form. We have an upper triangle because all the entries below this main diagonal, all those entries are now 0. And so now we have one more step to take. So determinant A is going to equal negative 3 times negative 55 times 1. And you're like, what? How did I get 1 from this matrix? Well, don't forget your theorem 2.1.2, which says if A is an n by n triangular matrix, upper triangular, lower triangular, or diagonal, then the determinant A is the product of the entries on the main diagonal. So 1 times 1 times 1 equals 1. So now I'm ready to go ahead and solve this bad boy. So the final determinant of this matrix is going to be negative 546. Wowza. So we got there. I'm sorry. What am I saying? It is not that. I have done bad on my math. Ignore that. The final grand total of this is 165. So in example 3, we've made good use of using row reduction to the row echelon form of a matrix in order to get to our determinant value. And so we're going to look at another cool example, example 4, where we're going to do another cool little trick here. So don't forget how special our upper and lower triangulars are, because we're going to want to make use of them in order to evaluate our determinants. Now with example 4 here is the matrix that we're faced with. And so you might be thinking to yourself, okay, well, if we did like example 3, we'd be going through these different elementary row operations and we try to reduce A to row echelon form. But really, there's an easier way to do this in one step. And so that step is, can you guess? And so what you're going to want to do is you're going to want to add negative 3 times this first column to the fourth column. So here we're actually doing column operations. You're like, what? My mind is blown. I'm always used to row operations, but now we're actually doing column operations. So I'm adding negative 3 times this first column to this last fourth column to obtain this new matrix to be able to determine the determinant. So we want it to be now this new matrix here, 0, 7, 6, 3, 0, 0, 3, 1. And now we have 0, 0, 0, and this last entry is negative 26. Because if you think negative 3 times 7, which is negative 21, plus the negative 5, that's going to give us negative 26 there. Lo and behold, what do we have? We have a lower triangular form now in one step. So you didn't realize this before, but now we can actually do column operations as well as row operations. So now we have a lower triangular here. And so now, guess what? Since we have this lower triangular, guess what? We get to multiply the entries along that main diagonal to determine our determinant. So here we have, this will equal 1 times 7 times 3 times negative 26. And here's where you're going to equal negative 546. So that will be the value of your determinant for this matrix. So keep that in mind. We are now introducing the fact that we can do column. So look up here, column operations. You thought there was just row operations. There are now column operations. So when you go back to that table, you're like, wait, we were relating everything to that table 1. Well, just realize that those things that you can do with rows, you can think about as well for columns. So whenever you multiply a row and add it to another row, or whenever you multiply a column and add it to another column, then the determinant of B is going to equal the determinant of A. So that's going to correspond to that third relationship in table 1. So think about that. We're now introducing the fact that we can do row and column operations. So example 4 is cool, all one step. So think to yourselves, if you have to calculate a determinant, you're going to be looking at several things. You're going to be looking at, does it have a row of zeros or column of zeros? Well, better look for that, because if it does, I know my determinant is already just 0. And then I'm going to make use of those relationships in table 1. I can also reduce my matrix to row echelon form. And that's going to help us to get to a determinant, right? And then now we've had the introduction of the column operations. And then also don't forget about your elementary matrix properties and how that relates to their determinant. So we got a lot of stuff going on that you'll want to be able to recognize by sight. So let's look at one last example for this section. We'll look at example 5. And here's where they have done a combination now of row operations and cofactor expansion. So we are once again trying to evaluate the determinant of A. So we have a very big matrix for example 5. Alright, so for example 5, I had to pause a minute and rearrange this a little bit so you could see it. So in example 5, we start off with a matrix that looks like this. Got 3, 1, 2, 3, 5, 2, 4, 7, -2, -1, 1, 5. Then we got 6, 1, 5, 3. So quite the matrix here. And so, like I said, example 5 is going to be a big old combo. So we're going to be mixing our row operations with our cofactor expansion that we learned in the last section. So to get to this matrix here below, we had to do some row operations. So basically, we're adding different multiples of the second row. So we took this second row here, and we added suitable multiples of it to the other rows to, reduce this down a little bit. And that way we had zeros starting off many of our rows. Keep in mind, this is not in reduced row echelon form yet, or row echelon form yet. We're doing some manipulations. So if we did -3 times this second row and added it to the first row, we got this one. And likewise with the other rows, if we did -2 times the second row and added it to the third row, we would have gotten this. And if we added -3 times the second row and added it to the fourth row, we would end up with 0, 1, 8, 0. So this is the matrix that results from suitable multiples of the second row to the other rows. So we end up with this more reduced matrix. So you might think to yourself, well, you know what, we don't have it in row echelon form yet. This leading one, it needs to be in the top spot. But if you remember from your last section, you're going to want to think to yourself, how can I strategically combine cofactor expansion with these row operations to get what I want to get to, and that is to figure out what is the determinant of A. Well, lo and behold, we have a very interesting property here. So we've gotten to this more reduced form so far. Like I said, it's not all the way to row echelon form. It's not all the way to reduced row echelon form, but it is more reduced than it originally was. But here's where you're going to realize that you're going to want to bring in cofactor expansion, because if you remember from our last section about cofactor expansion, ooh, man, we have a column that has a lot of zeros. And that was very, very, very helpful to us before, right? It's because that really eliminated a lot of our work. So we can ignore those zeros there, and we're just going to concern ourselves with this one spot. Because remember, with our cofactor expansion, this 0 ended up times, a submatrix, and the submatrix times that 0 ended up being a 0 anyway. So we didn't even have to worry about these places where there's zeros. So we're going to zoom in on this one spot of 1. We're going to do cofactor expansion on that. So here, we would want to do what? We're going to have to use that. So we're going to obviously get rid of our column 1 and our row 2, which is where that 1 is located. And we're now going to have a new matrix to look at in our progressive calculations of the determinant of A. Now, don't forget, when we're doing our cofactor expression, don't forget about that checkerboard. So when you're doing a checkerboard, this 1 is going to be in the negative spot here. So we're going to do a negative 1 times what we get for our new submatrix. Our new submatrix is going to be negative 1, 1, 3. We've got 0, 3, 3. And we've got 1, 8, 0. How cool is that? So we did what we call cofactor expansion. So cofactor expansion along the first column. So you're really going to want to practice these problems, because you're going to really want to recognize when you're going to do combinations of doing row operations and the cofactor expansion. And then that way you can get to calculating your determinant for your matrix much quicker. So now what we're going to do is we're going to go ahead and then guess what? We're going to revert back to our row operations. And we're going to add this first row to our third row. So now we're going to get negative 1 times negative 1, 1, 3. And we have 0, 3, 3. And now we have 0, 9, 3. So keep in mind that was adding this first row plus our third row. And now we got this new matrix here. So now we went back to row operations. Right? So see how we're doing this big old combo? And then now, guess what? We're going to go back again. We're going to realize that this is a great column to look at because it's got 2 zeros in it. So now we're going to go back to cofactor expansion along this first column. And so now we're going to get even further in this business. And now we've got a lot going on here. So we now are going to eliminate this first row and this first column. And so now we have negative 1 times negative 1 times the new submatrix of 3, 3, 9, 3. And then now we have a simple determinant calculation. So we have negative 1 times negative 1. And then we can easily take the determinant in this 2 by 2 matrix. So then we have 3 times 3. 3 times 3 minus 3 times 9. And then that in itself is going to equal negative 18, right? That's going to be 9 minus 27, so we'll have negative 18. So negative 1 times negative 1 is 1, and then 1 times negative 18, that's going to give us a grand total for this determinant of negative 18. Woohoo! So that was quite the process of using row operations in combination with cofactor expansion. So that will conclude our section 2.2 discussion of the examples in the section. And next class we'll continue on with section 2.3.